This illustrates the traditional castle and moat topology, a heavily fortified perimeter keeping threats out, leaving the internal network open. The fatal flaw is implicit trust. If an attacker bypasses the firewall, the system assumes they belong, immediately granting broad access to internal resources. Security telemetry from 2024 reveals that once an initial intrusion occurs, the average e-crime breakout time is just 48 minutes. In some cases, advanced ransomware can achieve full encryption in just 18 minutes. Attackers achieve this speed through a technique called lateral movement. Because the internal network lacks barriers, a compromised low-level endpoint, like a receptionist's laptop, acts as an unobstructed highway, allowing the attacker to move east-west across the network to reach sensitive financial or human resources databases. Building a thicker perimeter firewall offers zero mathematical advantage. If an attacker possesses a single valid credential, they bypass the outer defenses entirely and operate with the freedom of the castle. The rapid adoption of cloud computing, software as a service, and remote work physically dissolved whatever remained of the corporate network boundary. Corporate data is now accessed from home networks, public internet connections, and personal devices. Legacy virtual private networks attempt to secure the scattered workforce by routing remote traffic through a central server. However, VPNs operate on the outdated perimeter model. Once a remote user authenticates, the VPN grants them overprivileged network-wide access, creating a single point of failure. Solving this requires abandoning the perimeter entirely. Zero-trust architecture re-engineers the network's logical layout to remove internal trust zones, subjecting every packet to the same rigorous validation regardless of its origin. The entire framework operates on a single axiom: never trust, always verify. In a highly distributed ecosystem, defending a physical perimeter is impossible. The security model must shift to protecting individual resources, validating every single request as if it originated from a hostile network. The NIST SP800-207 architecture divides a network into two layers, the control plane at the top and the data plane below. Its core mechanism is the strict decoupling of logic from execution, isolating policy decisions from network traffic. When a user requests access, it hits the policy enforcement point, a strict gatekeeper unable to evaluate requests. Instead, it routes the request up to the policy engine, which dynamically evaluates the user's identity, location, and device health. If approved, the policy engine signals the policy administrator. It then commands the PEP to open a secure, encrypted microtunnel between the user and their requested resource. This connection is granted strictly per session. The moment the user completes their task, the tunnel collapses. Trust must be continuously re-established for every subsequent action. With the control and data planes decoupled, a malicious payload inside the network lacks any structural pathway to rewrite the rules governing its access. Zero-trust engineering operates under the assume breach protocol. Architects design systems with the absolute certainty that attackers are already inside the network. Organizations utilize microsegmentation. As shown here, the open network is divided into highly isolated, identity-based zones, effectively turning the network into a submarine with watertight compartments. If an attacker compromises a user's credentials, their access is confined entirely to that single microsegment. The physical isolation chokes off their ability to move laterally to adjacent systems. Field data demonstrates that implementing microsegmentation within a zero-trust architecture reduces incidents of lateral movement by up to 90%. A 48-minute breakout window poses a catastrophic threat, but locking an attacker inside a heavily restricted compartment completely neutralizes their ability to inflict systemic damage. Executing this architecture requires administrators to replace broad firewall allowances with highly granular, dynamic access rules. This table maps out the Kipling method for defining least privilege access. It dictates exactly who is requesting access, what data they need, when they can connect, where they connect from, why they need it, and how it's secured. Applying these strict parameters is challenging in older environments. Pre-2010 legacy systems often rely on hard-coded credentials and lack support for modern multi-factor authentication. To secure these vulnerabilities, engineers deploy identity-aware proxies. These act as modern security wrappers, enforcing strict multi-factor authentication checks before a user is allowed to interact with the legacy application code. Similarly, low-compute Internet of Things devices are integrated into the architecture through new industry standards like Matter, assigning unique cryptographic identities to sensors and mechanical actuators. Zero Trust is a universal methodology. It enforces the same rigorous verification on a legacy server room as a cutting-edge cloud deployment. Organizations with mature Zero Trust save $1.76 million per breach, generating a 312% ROI. This return results from rapid threat identification. Constant re-verification drastically reduces the mean time to detect a breach from 287 days down to just 24 hours. By 2026, this detection capability will scale through the integration of agentic AI. Agentic AI shifts machine learning to active execution. It identifies anomalies in milliseconds, autonomously rewriting firewall rules and isolating compromised users without human intervention. Integrating this intelligence transforms Zero Trust from a rigid set of validation rules into a highly active, self-defending architecture. This dynamic adaptability is critical for the coming decade. Quantum computing is projected to break the current RSA and ECC encryption standards that secure global data traffic. To prepare, Zero Trust architectures are building in cryptographic agility, deploying hybrid models that integrate post-quantum cryptography standards, so algorithms can be swapped instantly as threats evolve. Ultimately, the purpose of Zero Trust is to engineer long-term organizational resilience. It accepts the mathematical certainty that network breaches will occur, and focuses entirely on limiting their blast radius. In a highly distributed digital ecosystem, the physical perimeter is irrelevant. Identity is the new perimeter. Continuous, dynamic verification is no longer an optional IT upgrade. It is the only mathematical guarantee of network survival.